we've also seen two specific logics. We've seen the linear time temporal logic, LTL, which talks about time. And we've also seen Hoare logic, which talks about preconditions and postconditions. Now, before we can actually automate or half automate the reasoning about these logics in Coq, we need to go ahead and learn a little bit more Coq. So today I'm going to basically teach you the very fundamentals of functional programming. So most students in this course said that they haven't taken a functional programming course before. If you've already taken a functional programming course, if you've coded with Haskell or anything like that, this is going to be pretty trivial for you. Okay, but then hopefully from Thursday onwards, we can really move to doing proofs in Coq again. Okay, so let's start. And by the way, all of my examples are taken from Michael Clarkson's book. So all the credit goes to him. Let's just create a new module and let's talk about lists and pairs and things like this, which are standard in a lot of programming languages, but we want to see how we can define them in Coq. Now, the Coq standard library already has these things. That's another reason why I'm creating a module here, because I don't want to have a clash between the definitions, but I'm just going to show you how these things are actually defined and how they actually work. Okay. First of all, let's say that I want to have a type in which every element basically consists of two natural numbers. So I want to define a type that captures pairs of natural numbers. And I'm going to call my type natprod. And I'm going to define it exactly in the same way that I define any other type. So I'm going to say this is an inductive definition. The name is natprod. It's of type. So I'm defining a type. And it has only one constructor, and the constructor is called pair, and it takes two integers, n1 and n2, and they're of type nat. Well, not integers, but natural numbers. Okay, and that's it. So that's how I define a pair, basically. Now, I can, of course, define a function which returns the first element of my pair and a function that returns the second element of my pair. This is pretty easy, just using pattern matching. So let's say I have a function first, and let's say that it takes one of these pairs. It takes a natprod, and it has to return a natural number. Now, what I do is that I basically do matching on P, because that's the only thing I can really do. And remember that my type natprod had only one constructor, pair. And so when I'm matching P, I have to match it with some expression of this form, pair xy. That's how I can destruct P, basically. And so I say if P is the pair xy, then the first element of P is, of course, x. So I'm going to just return x. So it's a pattern matching with only one pattern, very easy. And the same thing happens when I want to get the second element of my pair. So let's say P is a pair of natural numbers again. I do the exact same thing. I match P, and this time I return y. Now, the one small difference here is that I'm using an underscore because I don't care about what this first value is. And of course, here I could also use an underscore for the second value because there I didn't care what the second value was. Okay. And of course, I can combine these functions together. So I can, for example, have a pair of two natural numbers, 4 and 1, and I can apply the first function on it. And you know that we have to write compute if we want to actually compute something. So I'm computing the first coordinate of the pair 4, 1. And of course, this should be 4, and it's 4, and it's of type nat. But of course, I don't like to write pair all the time. So I just define a very simple notation so that I can just use parentheses instead of pair. So I just define notation. You've seen this before. You've seen how we can define a notation and basically syntactic sugar in Coq. I'm not going to go into details of this, but basically what it says is that if you see some expression of this form, x comma y in parentheses, what that actually means is pair xy. And now I can write something like this. I can write compute first of 2, 3. And this entire thing is considered to be a pair. So it computes it and it's like 2. I can do other things, other interesting things. Let's say that I have a pair and I just want to swap the two coordinates. This is a very easy function to define. So I'm going to just define swap pair as a function that takes a pair P. So P is of type NAT_prod, and prod is for product basically, and it also returns another pair. And it just does pattern matching, very easy. If it matches the pattern XY, I'm going to return YX. So I'm just going to swap the coordinates. Now I have a trivial theorem that I want you to prove. So please prove this theorem. It says that for every pair of natural numbers, for all n and m that are natural numbers, the pair nm is the same as the pair consisting of its first element and its second element. So nm is the same as first of nm and second of nm. So the proof is super easy. I have to prove this. This is my goal. Let me move these things out of the way. So let's say I just apply simplify. If I apply simplify, what happens? Well, it just simplifies first of nm, but first of nm is just n. And it also simplifies second of nm, but that's just m. So if I do simplify, I just get this. I get that for all n and m, nm is equal to nm. And at this point, I can just do reflexivity. Okay. But as I've told you before, reflexivity is actually quite good at its work. So I can just write reflexivity, and it already also does simplify and so on. So for the proof here, I could just say reflexivity. Okay. Now I want you to try to prove this second trivial theorem, which basically says that for all pairs of natural numbers P is basically first of P, second of P. So every pair is a pair of its first element and its second element. So it looks very much like the trivial theorem before, but I want you to prove it now. Let's see what happens here if I want to do the same proof as before. So remember that before my proof was just to say simplify and use reflexivity, okay? So let's say I say simplify here. This is what simplify does. It basically does nothing because it does not know how to simplify any of these expressions, okay? And also if I say reflexivity, that's going to fail, okay? Because Coq is not smart enough to understand how it can apply reflexivity to the two sides of this equality, because they don't really look like each other in terms of their structure, right? They're syntactically very different. So Coq doesn't know how to do this. So instead, let's actually do a proof. So our first step is always to do intros because we don't want to have quantifiers in our goals. So I do intros P goes up, it's introduced now. So now I can say, let's destruct P here. Because P is a pair, and I know that it has this format, basically. It's like of type NAT_prod, so it's of the format pair N1, N2. So I can destruct it, and if I destruct it, I can also say destruct it as NM. I can just say destruct P, but I like to give names to the variables that I get after the destruction, so I do this, and now it writes P as NM. So this was P, I destructed it, it's now NM. But it also happens on the right-hand side. Here I had first of P and second of P, but now when I'm destructing it, I have first of NM and second of NM. And at this point, you see that this is the previous trivial theorem, basically. I just needed to do a destruct. So I can just apply the previous theorem, or I can just write the proof that I had for the previous theorem, which is simple and reflexive. Okay. Great, and that's it. So we proved two really trivial theorems here. But this is how we generally define pairs of items. If I want to have a pair of two items, that's what I do. But now let's say that I want to define a list of items. So how do you define a list? Again, the only way that we have in this programming language is to define new types. And we have this kind of inductive structural definitions for new types. So I'm going to define a new type called NatList, which is basically a list of natural numbers. So a list of elements, and each element is a nat. Now, what is a list? A list, I can say, is one of these two cases. It's either empty, which I show it by nil. So I'm defining nil, and in my mind, that corresponds to the empty list. Or it's basically consisting of two parts. The first part, I call it a head, which is like the first element of the list. Or actually, if we use indices starting from 0, it's the element at position 0. And then I have a tail, and my tail is the rest of the list. Okay? So my list is going to consist of a head, which is a natural number, and a tail, which is itself a list of natural numbers. But of course, I have to give a name to this constructor, so I just call it cons. Because I'm putting these things consecutively or whatever. I can give it whatever name I like. I like cons. Okay, that's also the standard name that is given to this in the standard library. So we do this, we defined this new type, which is called NatList. And of course, I can now use this new type to basically have variables of this type and also save lists. So if I want to have a list that has 1, 2, 3 in it, this is basically what I do. I say, this is my list. So remember, cons basically glued one element at the beginning of a list. So I'm gluing 1 at the beginning of a list, which is obtained by gluing 2 at the beginning of a list, which is obtained by gluing 3 at the beginning of the empty list. And so this is basically the list 1, 2, 3. And now I can say print this example list. And as you see, this is my list, and it's of type NatList. Now, of course, I hate to write things like this, so I'm going to define some notation so that I can work with my lists more easily. So the first notation I'm going to define is this. Instead of writing cons XL, I want to just be able to write X and 2 colons and then L. So this just means gluing X at the beginning of L. Okay, so I define this notation and I say whenever I write this part, what I actually mean is cons XL. Now I'm having some extra information here. Again, this is not something that we would cover in this course, but basically whenever you're defining a notation like this, you have to also give some extra information. One information you have to give it is about the order of the operators. Okay, so for example, if you're defining plus, minus, and let's say this glue operator, what is the ordering if someone writes an expression that has all of them in it, right? And here I'm basically saying that this particular operation is going to be at level 60 of my ordering, okay? And then the second thing is that what happens if someone writes something like this? How should I put parentheses for this? Okay, so I can think of this as first gluing A to B and then gluing the result to C, or I can think of it as first gluing B to C and then gluing A to the result. Okay, so basically the question is, what kind of associativity do I have? And here I'm saying you have right associativity. So if someone writes ABC without the parentheses, this is the meaning of that expression. Okay, but again, this is just defining notation. It's not that important. I also want to define these empty brackets to mean the empty list. So I just say whenever I write this, what I actually mean is nil. Okay, and I also define a notation like this. And this is a little bit more complicated, but it basically says if you have a sequence of items and you write them like this, what you actually mean is a list that is obtained by applying cons to every single one of them and at the end applying nil, right? So if I define this, basically these are the kinds of expressions that I can write. So I can say my list L1 is 1, 2, 3, basically, like this. But I can also write it like this. I can write it as 1, 2, 3 nil. So L1 and L2 are basically the same thing now. But I can also write it like this. So again, all of this is just syntactic sugar. From the point of view of Coq, when you are actually doing reasoning, the only things that you have are your constructors. You have nil and you have cons. It's just that we're defining some syntactic sugar so that we can write it in a nicer way. Okay. So now if I say print L3, you see that it also uses the syntactic sugar when it's printing it. Okay, and if I print L1, it's also the same thing. It's 1, 2, 3, which is a list of natural numbers. Okay, let's write some functions with this. So the first function I want to write is a function that basically takes some natural number n and repeats it for a number of times. So this is going to be called repeat. It takes two parameters. The first parameter is the number n, which is a natural number, and the second one is how many times it has to repeat it. It's called count, and both of them are natural numbers, and this function returns a list of natural numbers, right? And again, this is the most common thing that we do pattern matching. So I say, let's do a pattern matching on count. If it's 0, or actually, you know that instead of 0, I can also write O for natural numbers. So if it's 0, just give me the empty list. And again, this empty list, this is the notation that I defined here. So actually, what this means is give me nil, right? But anyway, 0 is a notation for O, and this is a notation for nil. And I say that if count was the successor of count prime, so count is count prime plus 1, then take n and glue it at the beginning of a list that you get from repeating n count prime times. Okay, so count prime is count minus 1, basically. So I create a list that has n count minus 1 times, and then I put n at the beginning of that list. Okay, so I can do something like this. I can do compute repeat of 1, 5. Okay, and this is what I get. So it just repeats 1, 5 times. Okay, now I want you to think about this next function a little bit on your own. So let's say that I want to have a function that takes a list and returns the length of that list. Okay, so the parameter that this function takes is some parameter L, which is of type natlist, but it has to just return one natural number, which is the length of the list. So write this function. So what we can do, as usual, is that we can just do pattern matching. And I have just one parameter here, which is the list L. So I do a pattern matching on L. Now, L is a nat list. So I had two different constructors. I had nil and I had cons. And I have to cover both cases when I'm doing pattern matching on L. So I say if it's nil, again, remember that this was just syntactic sugar for nil. I have the empty set, the empty list, so I just return 0. But if it was the result of cons of some element, some head and some tail L prime, then I just take the length of L prime and I add 1 to it. And the way I add 1 is that I can take the successor. Okay. So, of course, instead of this, you could also write 1 plus length of L prime or length of L prime plus 1. But by now, you've seen a lot of proofs and you know that it's easier if I just write S of length of L prime. So that later on, when I use this length in my proofs, simplify, I can easily simplify it. Okay. So this is the definition of length. Of course, I can use my notation here as well. So I can say if it was a head glued to an L prime, do this. So I could write cons, I could write it like this. I can put an underline here because I don't care about the value of h. All of these things work. Okay. So as an example, I can compute the lengths of repeat 3, 4. And of course, since I repeated it 4 times, the length is going to be 4. I can also compute the lengths of something like this. So I just give it a list and I ask, what is the length? It says 5. Okay. Now, next one, write a function that takes 2 lists and appends them together. So gives me a list that is basically the first list followed by the second list. So this function should take 2 parameters, L1 and L2, and both of them are lists of natural numbers, and it should return another list of natural numbers. Look, as before, we know that we should actually do pattern matching, but which one of these parameters do you want to do the pattern matching on? Do you want to write match L2 with something or match L1 with something? Why do you prefer pattern matching on L1? Yeah, well, in some sense, if we go back and see how we defined our list of natural numbers, our intuition was that we have this cons constructor, which basically adds some number n to the beginning of a list, right? So in some sense, it feels intuitively correct that it's easier to add something to the beginning of a list. So here, if I want to append 2 lists, L1 and L2, again, intuitively, I would start with L2 and I would keep adding elements of L1 to the beginning of the list because this is easier for me. So I do a pattern match on L1 and I say, well, there are 2 cases. Either L1 is the nil list, it's the empty list, in which case I should just return L2, right? Or L1 is of this format. It's a head followed by a tail. And remember that the head is just one number, but the tail is itself a list of numbers, okay? And if it's a head followed by a tail, well, I first take that tail and I append it to L2. And then I put H at the beginning, okay? And again, remember that these 2 colons, they are actually syntactic sugar for cons. So what I'm writing here is the same as saying, if L1 is cons of HT, then do cons of H and append TL2. But of course, with the syntactic sugar, it looks much nicer. And it's much more intuitive for a human to understand this. I first append T to L2, and then I add the head at the beginning. Okay? So I can do some simple things. I can say append repeat 5 twice and repeat 1 4 times. So I get a list that has 2 5s and 4 1s. I can say append 2 lists and I can give the lists like that and it just appends them. I can also write examples and remember that an example was basically the same as a theorem. So every time you write an example, you have to prove it. So I can say that the append of 1, 2, 3, and 4, 5 is just 1, 2, 3, 4, 5. And the proof is very simple. I just say compute both sides, and they're the same. So do reflexivity. That's it. Now, I actually like to define some notation for append itself, because I don't like to write append all the time. So I'm just going to define plus plus to mean append. So this is the notation that I define. I say whenever I write x plus plus y, I actually mean append xy. And again, I say that it's associative from the right, and I put it at level 60. Okay. So we've talked a lot about head and tail here, for example, when we were doing append. So it's good to actually have functions for those. So let's say I define a function called head, which is supposed to give me the head of the list. So the element at index 0. If we think of our indices in our list starting from 0, I want to get that element. But now there is a problem here. And the problem is, what happens if my list is empty? So if my list is empty, there is no first element. Now, in a lot of programming languages, for example, let's say in C++, if you have an empty list, or let's say you have an empty vector in C++, and you try to access its head, you try to access the element at index 0, you will just get an error, or your program will be killed, or an exception will be thrown, right? But we can't have that here. Every function that we define here should always return something. I cannot have a case where my function just says, oh, I have an error, I don't return anything. So instead, what I do here is that I say, well, whenever you call the head function, you should also give me a default value. And I'm going to return this default value if there is no head. So my head function is not just going to take a list, it's also going to take a natural number, which is the default value that it should return if the list doesn't have a head. Okay, so the parameters are this default, which is a natural number, and L, which is a list of natural numbers. And of course, what it returns is of type nat. And now I can do a pattern matching on L, on the list. I say, if the list is empty, if it's nil, just return the default value. And if it's not nil, if it's of this form, a head followed by a tail. And again, remember, this is basically the same as const ht. Okay. Then in this case, just return the head. And of course, I don't even care about the tail, so I can just put an underline there. That's it. Now I can similarly define a function. Okay, before that, let's actually do some examples. So I can say compute the head of 1, 2, 3, 4. But I have to also give it a default value, and I say the default value is 0, which means if there is no head, just give me 0. Okay. And in this case, you see that it gives me 1 because 1 is the head. But if I say compute the head with the default value 0 of the empty list, it just gives me 0. Of course, I can change the default value to whatever I want, and it just returns the default value whenever there's nothing to return. Okay. We'll see a better way of doing this. Now let's define another function which returns the tail. Now, in this case, I don't really need a default value, right? So if I have a list of natural numbers and I want to return its tail, if my list is empty, I can say the tail is also empty, right? Because the tail basically says, what is the remaining list if you remove the first item? If the original list was empty, it makes sense to return the empty list. So I do this pattern matching and I say, if my list L is empty, just return the empty list. And if it's of this form, just chop off the head and return the tail. And again, here, since I don't need the head, I can just put an underline or underscore for head. So that's it. So now I have two functions that give me head and tail. But very importantly, my tail is not my last element, right? My tail is just all of the elements except the first one. Write a function that actually gives me the last element. So complete this function. I want to have a function called last element, which takes a list L of natural numbers and returns a natural number, which is the last element. And of course, it should also take a default value for the case where there is no element, there is no last element. So here's what I'm going to do here. I'm going to do a pattern matching on L. And I'm going to say either L is the empty list, in which case I just return the default value because there is no last element. Or it's a list of this format. It has some number n followed by the empty list. Okay, const of n and empty list. And I can also write it like this. Now, if I have this case, I basically have a list of just one element, that's n, and of course I return that as the last element. Or if it's of this format, it's n followed by a tail, right? And in this case, I just return the last element of this tail. But I have to be careful to pass the same default value to this function again. Okay? But very importantly, when I'm doing pattern matching, I check the patterns from top to the bottom, right? So in this case, the third pattern is checked only if the second pattern does not apply. So this pattern is actually saying that T is not empty. That's why I can go and take the last element of T. Okay? So I can have things like computing the computing the last element of, let's say, 1, 2, 3, and it gives me 3. Okay. Now I can prove some theorems. So the first theorem I want to prove is that if I have a list, LST, and I just append the empty list to the beginning, I'm going to get the same list LST back. Okay, so appending the nil list will not change anything. And here's my proof. I just say reflexivity, it solves it. Because if you just look at the definition of append, we can go up. And append already says that if you have an empty list, you just return the second list. So if I actually do this step by step, I can do this. I can say first do intros. And now here I have the empty list appended by LST. But if I do simplify, I already get LST on the left. And then these two are, of course, equal. So I can just do reflexivity. But again, just writing reflexivity would also solve it. Okay. This is the next theorem that I want you to prove. I want you to prove that if I have a list LST, the length of its tail is the predecessor of its length. So basically all I'm saying is that if I have a list of n elements and I chop off the first element, I will have a list of n minus 1 elements, right? But okay, so we've defined length, we've defined tail, and pred was a function that we defined when we were talking about natural numbers. It basically gives the predecessor of a number. Okay, try to prove this, but before you prove it, there is something strange about this theorem. It doesn't have a corner case. It doesn't say that it holds for all lists that are not empty. I'm saying it holds for every list, including the empty list. Why does that make sense intuitively? Because if I have the empty list, then the length of that list is 0. But I defined the predecessor of 0 to be 0 because I was just working with natural numbers. So I don't have minus 1. And also, if I have an empty list, I said that the tail of the empty list is the empty list itself. So if LST is the empty list, both sides are actually 0. And I don't need to have a corner case for that. So this is our goal. And as always, whenever I have quantification here, I want to get rid of it. So I do intros. Now I basically want to do a casework on my list. I want to say my list is either empty, it's the nil list, or it's non-empty, so it has the cons construct. So I'm just going to say destruct my list, and I'm going to give a name to my head and tail. So I'm going to call them H and T when I'm doing the destruct. So now I have two goals. The first goal is the case where my list was empty. So I have to basically prove this. But I can prove this by just computing both sides, right? So the length of the empty set is 0 and its predecessor is also 0. The tail of the empty set is the empty set, and the length of the, list, not set, and the length of the empty list is also 0. So I have 0 on both sides. So if I just say compute, I see I get 0 equals 0, and I say do reflexivity for that. Again, I didn't need to do compute first. I can just do reflexivity. It's smart enough. Okay, how about this one? So let's look at our goal here. Here I have the length of the tail of a list that looks like this, H followed by T. Okay, And on this side, I have the predecessor of the length of the entire list, H followed by T. So let me try to simplify this, and let's see what simplify gives me. It gives length of T on both sides. But let's understand what simplify is doing here. How do I get length of T on both sides? Well, on this side, I have the tail of this expression, but the tail of this expression is just T. That's the definition of tail. So if I go back to where I define tail, I said anything followed by T, I'll just return T. So when I simplify, of course, on the right-hand side, I'm going to just get length of T, right? Let's see. Yes. But I'm getting the same thing on the left-hand side as well. So what's happening there? There, I'm first applying the definition of length. So simplify is just applying the definition of length. But let's go back and see the definition of length. Again, in the definition of length, it says that if you are in this case, if you have some element followed by another list, just give me the successor of the length of that list. So this entire thing becomes the successor of the length of T. So I have the predecessor of the successor of the length of T. But then it applies the definition of predecessor, and it knows that the predecessor of successor of something is just that thing. So that's what's happening in just one simplify. That's all the steps of simplification that gives me length of T on the left-hand side. So now finally I have length of T on both sides. I can just say reflexivity, and that's it, QET. Okay, but these were basic proofs that we were doing on lists, and we were not using induction. Let's actually do some inductive proofs on our lists now. Here's the first theorem that I want you to prove. I want you to prove that append is an associative operation. So I want to say if I have three lists, I can first append list 1 and list 2 and then append list 3 to it, or I can first append list 2 and list 3 and then put list 1 at the beginning. And I want you to prove that these two are the same. We want to, of course, do induction, but which parameter do you want to induct on? Why?
That is defined on the first thing.
Yes. So we had this intuition from before that whenever we want to do induction, we want to apply our induction on the same parameter where we did our pattern matching in the definition of the operation that we're doing. So in the definition of append, going up here, where's append? I'm doing pattern matching on the first parameter. So ideally, I want to also do an induction on the first parameter here, which is LST1. So let's do this. I start my proof. Again, I have quantifiers here. I do intros so that I get rid of my quantifiers there. And then I say, let's do induction on LST1. Okay. And again, LST1, it's a list. So it has two possible constructors. This is what we have here. You have nil or cons. And what I'm saying here is that I'm saying, well, nil doesn't have any parameters, but for cons, give the names H1 and T1 to the parameters. So I'm saying do an induction on LST1 and use these names for the variables that you get there. Okay. So when I do this induction, as you see, I have two goals now. So the first case is the base case of the induction where LST1 was nil. And the second case is like the inductive step where LST1 is not nil. So if LST1 is nil, this is what I have. This is what I have to prove. I have to prove nil appended with LST2, appended with LST3 is the same as this expression. And by the way, you don't see any parentheses on the right-hand side here. And that's because when I defined the notation, I actually told Coq that this operation, this append operation is right associative. So Coq doesn't put extra parentheses when they're not needed. But if I want to see all the parentheses, I can just write this. I can write set printing parentheses. And if I do this, it now puts down all the parentheses, and you see that the right-hand side is actually different because of the parentheses. Okay, but let me not do that. Let's just work with this case. So now I can actually just do simplify again. Why can I easily do simplify? Because if I do simplify on this side, I know that it's the empty list appended with LST2. But in the definition of append, this would just give me LST2. So if I do simplify, I expect this expression LST2. And then on this side, I basically had the parentheses over this expression. So I have the empty list appended to whatever this rest of it is. But then I will just have the rest of it. So if I do simplify, I get the same expression on both sides, LST2 plus LST3. And now I can use reflexivity. Great. So my first goal was reached. I have one remaining goal, and this is the remaining goal. It says that you have this induction hypothesis, which is basically talking about the tail of the first list. It's saying that T1 plus LST2 plus LST3 is the same as T1 plus LST2 plus LST3 with different parentheses, of course. And then I have to prove the same thing, except that I now have H1. So again, I can do simplification. And if I do simplification, it uses the definition of append. Let's go back again to the definition of append. You see, it says that if you're appending some L1, which is of this format, a head followed by a tail, then you can just first append the tail and then put the head at the beginning, okay? So if I apply this simplification at this point, you see here, I have a head and a tail and I'm appending it with something. So I will just get the head appended with the tail and that thing. So I'll do simplify, and as you see, again, it just feels like we changed parentheses, but this is a different expression. Now what do I have? Here, I have T1 plus LST2 plus LST3. And by plus, I mean append. And here I have the same thing, except that it has a different parenthesization. But I already know that these two things are the same because of my induction hypothesis. So I just say rewrite using the induction hypothesis. And now I finally have the same expression on both sides. And I can say this is reflexivity. And okay. The next thing I want you to do is to write a function that takes a list and reverses it and just returns another list, which is the reverse of the original list. Okay, so as usual, the only operation that I can really do when I want to start writing my function is to do a pattern matching on the parameter. So I have this list LST and I want to reverse it. I say, let's do a pattern matching. There are two cases. Either my list is empty, in which case I have to just return the empty list and I'm happy about it. Or my list is of this form. It's H followed by T. And remember, H is just one element, T is itself a list. And if this is the case, what I'm going to do is that I'm first going to reverse T, and then I'm going to add H to the end of T, right? But crucially, I didn't have an operation that would just add one element to the end of a list. The only operation that I have, if I go back to the definition of my list, where is it? Here. The only operation I have is the operation that adds one element at the beginning of a list. But I've already defined append. So I can just create a list that has only one element in it, that only has H in it. And then I can append it to the end of this list, the list that was obtained by reversing T, right? So this is the same as saying I'm adding H to the end of T, but since I didn't have that operation, I had to just use append to do the same thing. So I do that. This is the definition of reverse, and now I can do computation. So I can say compute the reverse of 1, 2, 3, 4, and of course that's the reverse. It's 4, 3, 2, 1. And of course you could expect that I want you to prove this theorem now. So with this definition of reverse, I want you to prove that for every list, the length of the reversed list is equal to the length of the original list. Here's the proof. This is our goal. Again, as usual, we start with intros. Now I want to prove this. I want to prove that the length of the reverse of this list, LST, is the same as the length of the list itself. Now, of course, I have to do induction here, and I literally only have one variable, so I can just do induction on LST. And remember that our induction is always structural induction. So for a list, LST, we had two cases. It was either the empty list, nil, or it was one item added to the beginning of another list. So when I do induction on LST, it gives me these two cases. The first case is where LST was empty, and the second case is where LST was basically something like this, n followed by some other list. Actually, let me say, in this case, call it head and tail. Now, for the first case, I can just use compute, because this is the length of the empty set. I don't know why I keep saying set. This is the list of the length of the empty list. And I just compute it and it's 0, right? And I can also compute the reverse of the empty list, which is the empty list, and then its length is 0. So I just say compute, and I get 0 equals 0, which is reflexivity. Great. Now I have the inductive step. So this is what I know. I know that the length of the reverse of t is equal to the length of t, but now I have to prove that the same thing holds if I add one element at the beginning of t. So if I have h followed by t. Okay, so let's simplify. Now, again, what's happening when I'm simplifying here? Look, on the right-hand side, I had lengths of h followed by t. And simplify goes and looks at the definition of lengths. So it says if I have something followed by t, I just have length of t plus 1, s of length of t. Okay, and that's exactly what's happening here when I'm simplifying. I'm getting s of length of t. On the left-hand side, when I'm doing simplify, it's applying the definition of reverse. So what is reverse of h followed by t? According to the definition of reverse, this is the reverse of t appended with the list that has just one element, h. Okay, so I do this, and this is exactly what I get here. Now, what do I know from my induction hypothesis? I know that the length of the reverse of t is the same as length of t. Okay, so here I have length of t. Here I have length of reverse of t appended with something. Okay, so let's try to rewrite it using my induction hypothesis. And this is what I get. What I get is that the length of the reverse of t appended with h should be 1 more than the length of the reverse of t. Okay, so I have some list reverse of t, and I'm basically adding one element to the end of this list, and I want to say that the length is going to increase by 1. Now, this seems to be a very simple thing. You might think that if I just write reflexivity, it would work, but no, it doesn't work, right? Why doesn't this work? Well, the same way that I could say set printing parentheses, I can say set printing all. And what this does is that basically instead of using the syntactic sugar, it prints everything in detail so that you can see what you have on each side. Now you see from Coq's point of view, this is what I have. So this one on the left-hand side, it's the length of the append of the reverse of t and the list that is just cons of h and nil. So this is the list that only has h. Now, so if I want to do simplify, or if I want to do reflexivity, they both fail. Why do they both fail? Because Coq cannot really simplify this at all. So I have the length of something appended with something else, right? If I go back to the definition of length, you see I have two different operations, and these are not the same operations. I have the append operation, which basically takes two lists and glues them together. And I have the cons operation, which adds one element at the beginning of a list. These are not the same operation because of the differences in the types, right? One of them is adding one element to a list. The other one is adding two lists together. So my problem is that length is using this one in its definition, but what I need here is the length after append. So that's why I cannot move forward in this proof. I get stuck here. And from Coq's point of view, these are completely different, of course, because Coq doesn't have the human intuition that we have. It just looks at all of these things as a bunch of functions and just follows the rules. Again, if I print it, you see that it sees it as the length of the append of this and cons. And for Coq, append and cons are different. And also, other than that, another problem that I have is that I'm not really adding this to the beginning of my list. I'm adding it to the end of my list. So even if I didn't have append here, I had something like cons, I would still have the same problem, because in the pattern, when I was matching for lengths, I had the case where I had something added at the beginning of my list, but this is now something added at the end of the list. So because of all these problems, this proof cannot go on, and I just say abort, I give up. Okay, so instead, what I'm going to do is that I'm going to first prove another lemma. And this is a very simple lemma that will hopefully help me solve this case. So remember, this is what I needed so that I can prove my previous theorem. I needed to prove that the length of some list, I don't care that that list was the reverse of T. The length of some list appended with one element at the end is going to just increase by one. That's what I want. But I'm just going to prove a much more general theorem. And what I'm going to prove is that if you have two lists, and if you append them together, the length of the result is the sum of the lengths. So let's try to prove this. Okay. So again, I have universal quantification here, so I do intros. Now, this is what I want to prove. As usual, I want to do induction. Now, again, I do induction on LST1 because LST1 is on the left-hand side, and I again have this intuition that I want to make sure that my induction matches my pattern matching in the definitions. So I do induction on LST1, and I say, break it down into head and tail, H1 and tail 1. So this is the first case where my LST1 was basically the empty list. And basically it says that the length of the empty list appended with LST2 should be the length of the empty list plus the length of LST2. But here I can use simplify. And if I use simplify, it uses the definition of length to see that this is 0. Okay. And it also uses the definition of append to see that this is LST2. So when I do simplify, I get length of LST2 on both sides, because this is length of LST2, this is 0 plus length of LST2, and it also uses the definition of addition. It knows that 0 plus something is just that thing, right? So simplify gives me length of LST2 on both sides, and then I can say reflexivity, and that's my first goal. Now I have one remaining goal, and this is the induction step. So let's say that the length of T1 appended with LST2 is length of T1 plus length of LST2. Now, instead of appending T1, I'm appending H1 T1 to LST2. Okay, again, let's see what happens if I do simplify. If I do simplify, it uses the definition of append, and it sees that appending H1 T1 to LST2 is the same as taking H1 and taking the result of appending T1 and LST2, so this, and then putting H1 at the beginning of it, right? And then it uses the definition of lengths to see that that's 1 plus the lengths of the append of T1 and LST2. So you see when I do this simplification, it basically gives me 1 plus the lengths of append of T1 and LST2. And remember, S was basically the successor. That's what we have. And then what happens on the right-hand side? On the right-hand side, it can't really do anything with this one, but it can simplify this one. It can say that, well, the length of H1 followed by T1 is 1 plus the length of T1. So when I do simplify, that's what I get. But then it also does one more step, and it's like it was S of length of T1 plus length of LST2, but it understands that applying the definition of addition, that's just the successor of the addition of both of them. So it's whenever I'm doing simplify, I'm applying all of these definitions. Everything that we've defined before in the previous sessions, for example, addition for natural numbers, is also used here. Okay, now this is what I have to prove. But this is quite easy, right? Because here I know that length of T1 plus LST2 is the same as length of T1 plus length of LST2. And all I have here is that the successor of the first one should be equal to the successor of the next one. So I can just do rewrite. And by the way, I can do the rewrite in any direction here. It doesn't matter. I can do this rewrite, or I can do this rewrite. And in both cases, I get the same thing on both sides. So I can just say this is reflexivity and QET. Okay. Actually, I also need another lemma, but this is a lemma that we've proven before. And it just says that if I have two natural numbers, A plus B is equal to B plus A. So addition is commutative. I've proven this to you before, so I'm just going to go over it like that. When you're writing this, you can just write admitted. Right? So A plus B is B plus A. We've proven that before. Finally, we can come back to the theorem that we wanted to prove. We wanted to prove that for every list, the length of its reverse is equal to the length of the list. So let's do the proof again. And this time we will not get stuck. So I first want to get rid of this quantification. So I do intros. Then I do induction on my list. And of course, I break it down into a head and a tail. Now, the base case is when my list is empty, I can just do compute here, and it gives me 0 equals 0, which I can solve with reflexivity. And now I have one goal remaining. And the goal that I have remaining is this. This is the inductive step, basically. So let's do simplify. This is the same as before. And this is where we got stuck last time, right? But now I have this theorem, which says that whenever you're appending two lists, the length of the result is just the sum of the lengths. So I can rewrite using that theorem, and it will rewrite this part, right? So let's do it. So now instead of lengths of this append, I just get the lengths of the two. Okay. Now I can do simplify. Now what happens if I do simplify? You see, it just applies lengths to this. But this is a list with only one element. So length just returns 1 already for this. So if I do simplify, length of H will be replaced by 1. So I do simplify. Now this is all I need to prove. I need to prove that length of the reverse of T plus 1 is equal to the successor, which is also plus 1 of length of T. But what is my inductive hypothesis? It's that T and its reverse have the same length, right? So I just use my inductive hypothesis to rewrite my goal. Instead of length of reverse of T, I will get length of T. So this is what I have. I have length of T plus 1 is the successor of length of T, right? But remember, successor of length of T wasn't really length of T plus 1. It was 1 plus length of T. And these two things are different for us, right? So this is why I needed this other lemma, which basically said that I can change the order of addition. So now I can rewrite using that. And instead of length of t plus 1 on the left-hand side, I get 1 plus length of t. And finally, here I can use reflexivity, or actually I can use simplify first. So because simplify uses the definition of addition, and it sees that 1 plus length of t is the successor of length of t, right? And then finally, I have the same thing on both sides. So I can say reflexivity, and this ends the proof, and it also ends this session. Okay, see you after lunch. Make sure that you write everything that I write here, because at some point I will ask you to prove something and you already need to have the definitions. So if you need time, just tell me and I will wait a little bit after each one of these. Okay. So we've already talked about lists, and we talked about these two functions that basically return the head of a list or the last element of a list. Now, let's say I want to write a function that basically takes a number n and a list LST and returns the item at index n, the nth item of the list. And I'm assuming that my list starts with index 0. Okay. So I'm going to call this one nspat because it's a bad function. We'll see why. But basically, this is what I'm going to do. So I have an LST, which is a list of natural numbers, and I have an index n, which is itself a natural number. And of course, my function should return a natural number as well. So I say, let's look at my list. Let's do a pattern matching on LST. And first of all, if my list is empty, I'll just return 0. Okay. And this is the part where returning 0 is not a great idea, right? Because I cannot distinguish between the case where my list didn't have an nth element and the case where the nth element was actually 0. Now, of course, I can do the same trick as before. I can say, give me a default value and I'll return that default value, but that's also not a great option. Anyway, for now, let's say that this is what I do. If my list is empty, I just return 0. Otherwise, my list has to be of this form. It has to have a head element followed by a tail list. And now I'm going to say, let's do a pattern match on the second parameter, on n. If my n is 0 and I have a head, of course, I'm going to return the head because that's the one at index 0. Otherwise, my n is, let's say, k plus 1. N is s of k. So I basically have to look at my tail, and I have to return the kth element in the tail. So in this case, I just call the same function recursively with parameters t and k. Okay, nice. So now the problem, of course, is that I have this case here, and I'm returning 0, and 0 doesn't really mean anything. I could have returned anything else. But nothing would solve my problem, no matter what value I put here. Even if I put, let's say, 42 or whatever, 420, I always have this really bad situation where I cannot distinguish between the case where my nth element was actually this default value and the case where my array or my list actually had less than n elements, right? So let's say I want to somehow distinguish between that. The way I can do that is to define a new type, and I'm going to call this type an option. Now, this is how this type looks like. So it's an option on natural numbers, so I'm going to call it nat option. It's a type, and it has two constructors. The two constructors are none and sum. And I mean, I can put the none first, or I can put it second. Who cares? Let's actually put it first. Maybe that's a little bit more natural. So I can have none or sum. And basically, this is a new type. Nat option is a new type that has two different constructors. So you can have none, and we think of none as something that doesn't exist. So think of how you work with null pointers, for example, in C++. When I don't have something, I say it's none. Or if it's not none, then it's something. So I'm going to call it sum. And then sum is going to also carry with itself a natural number. Okay. Now, very importantly, this is a different type than the natural numbers. This is a completely new type that I'm defining. So now what I'm going to do is that I'm going to define the same function that took an array, or sorry, took a list. I don't know what the problem is with the word list. I always say set or array. It's a list. So whenever I say set or array, just think about list. So I just have a bug in my mind. This function is supposed to take a list, LST, and some index n, and return the element at the nth position. But you see, instead of actually returning a nat, a natural number, I'm going to return a nat option. Okay, so the nth element, if it doesn't exist, I'm going to return none. If it does exist, I'm going to return some and that element. Okay. Now, why is this better than just allowing my functions to have errors or anything? Or why is this better than having, let's say, a null value, null pointers? I could just define my natural numbers to also have a null value, right? This is better because now I have these two different constructors for the option, which means that whenever I'm working with a variable that is of type nat option, and whenever I do pattern matching, I am forced to consider all the patterns. Remember, so one of the rules in pattern matching was that you have to cover all the possible cases. So this actually stops me from writing code that forgets about none. Whenever I write any piece of code that is working with a nat option, I am forced to consider the case where it's none. So this effectively means I will never have things like null pointer errors. That's not going to happen to me because every time that I match, I'll have to consider the case where it's not. Okay, so this is just a better way of coding where you don't have these kinds of errors just by the way that the language forces you to code. Okay, let's actually write this function. And this is like the standard library name of this function. It's called nth error. And basically it takes a list, it takes some number n, and it returns the nth element of the list. And it returns an option. So if the nth element does not exist, it returns none. If it does exist, it returns some and the element, okay? So the function itself is actually very much like the previous one, except that we have to make some small changes to make sure we have the right types everywhere. And instead of the default value, now we have none. Okay, so I'm going to start with a pattern match on my list. And I say, if my list is empty, just return none. Because there is no element in an empty list, there is no nth element in an empty list. Otherwise, my list is of this format. It's a head element followed by a tail list. So in this case, I say, let's do a pattern match on the natural number n on our index. If our index is 0, I just have to return h, okay? But remember, my return type is not nat, it's nat option. So I don't return h, I return some of h, some h, okay? In the other case, if my n is k plus 1, I just have to take the tail and I have to return the case element in the tail. So I just call the same function with parameters t and k. Okay, and that's it. By the way, one point that I'm not really talking about in this whole lecture is the runtime of these functions. We don't really care about that. We are focused on whether these functions are correct. Of course, you can have much more efficient implementations, and this is not a very efficient one. Okay, so let's actually do some examples of computations with this function, nth. So if I have this particular list and I ask for the element at index 0, it should give me 4, and it does give me 4. Okay, now let's say I have this one, which has only 4 elements, and I ask for the element at position 10. Okay, it gives me none. But again, I want you to really focus on the types. So here, it's not really returning the natural number 4, it's returning a nat option, which is sum 4. And this one is actually returning a NAT option, which is none. Okay. And of course, if I want to get this value of 4 out of the NAT option, I can again do a pattern matching. But then I have to say, do a match on this NAT option. And when I do a match on this NAT option, I have to consider all the possible cases. So the language forces me to consider the case where I have a none. Okay. Let's see how else we can write the same function. So here's another way of writing the same function. Let's say I have this list, which is a list of natural numbers, and I have n, and again, I'm returning NAT option. Instead of writing 2 matches like this, I can just write a single match, which works on both parameters, match on LST and n. So the first case is that if the list is empty, I don't care what n is, I'm going to return none. If the list has a head, again, I don't care what the tail of the list is, as long as n is 0. So if n is 0 and the list has a head, I just return that head, but of course I have to convert it to the right type. So I return some h, not just h. If I just return h here, you see that I'll get an error. And basically the error is that the term h has type NAT, but it was supposed to have the type NAT option. Whereas if I do some h, this works. And finally, the last case is that if none of the previous cases happened, so my n is k plus 1, it's the successor of k. And in this case, I don't care about the head of my list, I only care about the tail. I say, give me the case element of the tail. And this is a recursive function, and that's why we're using the word fixed point here. Okay. Have you all caught up? Do you all have these functions now? If you don't, please let me know. I'm going to wait for just 1 minute for everyone to catch up. And again, remember, this was the definition of our option. Let's actually define a partial map, or what you would probably know just as a map. So we already know how we can define functions. But the thing that we saw about functions is that we only have total functions. We cannot have partial functions in Coq. So your function should always return something. For example, here in this nth error, if I don't have one of the cases, if let's say I just remove this case, I will get an error, and it says that the pattern matching was not exhaustive. So my function, whenever I have, for example, a pattern matching, I have to have exhaustive pattern matching, which means I have to cover all the cases. And also in every case, I have to return something. So my functions are always total functions. There is no case where I give some inputs parameters to a function and it doesn't return anything. I cannot have that. Okay. Which also, by the way, means that I cannot write programs that run forever in Coq. Right? Just by the way that I'm writing my programs, the fact that I have to be able to verify that the functions always return something, that means that I cannot have an infinite loop. Okay, great. And even when I'm defining recursive functions like this, Coq checks, and I cannot have some infinite loop here. Now, let's do partial map. Let's say I want to have a function that maps elements of some type to elements of another type. For now, let's say I want to map natural numbers to natural numbers, but let's say I want to have a partial function. So I want to have something, again, like map in C++. If you have a C++ map, for some keys, you have values, but you don't have a value for every possible key, right? So I want to define a type that basically covers that kind of map, a partial map. So here's what I say. I say my map, which is basically a new type, and I'm going to call it partial map, very much like my list. It has 2 cases. Either it's empty, or I have a key k that is mapped to a value v, and then I have the rest of my map. Okay? So this is a definition of map, which is basically using the list as its underlying data structure here, right? So the only difference with what I had for list was that in list, so I had the empty list, and I had the list where I took another list and added one element. But now, here in this definition, I'm going to say that for a partial map, I have the empty map, and I have a map that is obtained from another map by just adding one key and one value to the beginning. I can give whatever names I want to these constructors, but the really important point is that these names should be unique. I cannot reuse the same names that I had for my list. So that's why I use empty and I use binding here, which basically means I'm binding the key K to the value V, and I have another partial map, which is the rest of my map. Okay, great. So here's a very simple operation. Let's say that I want to update the value of a particular key. So I have a key K, which is a natural number. I have a value V, which is a natural number. I have a map, M. And I want to return another map in which everything remains the same, except that K is mapped to V. So this is actually super easy. I can just use this second constructor. I can just say binding KV. I just add K and V to the beginning of M. No, yeah, that's an important point. If I have the same key already there, I'm not going to remove it. I'm just going to add this new key to the beginning. But then later on, when I search, I start searching from the beginning, so I will only see the first instance. Again, our data structures, especially in this course, they're not optimal at all. It's not about having the optimal data structure. It's just about being able to reason with these data structures. Speaking of which, complete this function. Let's say I want to do a search. I want to find a particular key. So this is the find function. It gives you a key. It gives you a map. You have to return the value corresponding to this key. But of course, the key might not exist in the map. So instead of returning a natural number, you're going to return a NAT option. And you have to return none if it doesn't exist. So intuitively, it's obvious what you have to do. You have to just read this partial map and write a recursive function, and you have to look at the first element, see if the first element has the right key. If not, you look at the rest of the map. And if there is no first element, if your map is already empty, you just return none. Okay, so let's do this. So I'm going to first do a pattern match on my map, M. And first of all, I'm saying if it's empty, return none. And remember that empty was a constructor in my partial map type, and none was a constructor in my NAT option type. And it's actually really important to give them different names. Okay, otherwise, my map is something like this. It's of this format. It has a binding. It's basically mapping some other key, let's call it K2, to V. And then I have the remaining part of the map, which I call M prime here. Now, here's what I do. I say, if K is equal to K2, if I have the right key, then return V. But in order to return this V, I have to turn it to NAT option, so I have to return some V. Okay. Otherwise, if it's not the right key, just keep searching for K in the rest of the map in M prime. Okay. Again, the types here are really important. First of all, I told you about the difference between equals and equals question mark. So I need a Boolean as my if condition so that this works. If I write it without the question mark, it gives me an error because it says K equals to K2 has type prop. It's a proposition. I cannot use that in an if. So I have to use equal question mark. Okay. So that's the first thing. The second thing is a very common mistake when people want to write this is that they focus too much on the pattern matching. So here's one way that will not work. So let's say I write the same function, find. It takes a key K, it takes a partial map M, and it's supposed to return a NAT option. Okay. And let's say I do the same match on my partial map M. So I say if M is empty, return none. Then I've seen this kind of code before, and it comes from a very common misunderstanding. I can say if it's binding of K, V, and some M prime, then return V. Otherwise, if it's binding of some other things and M prime, then return find of K in that M prime. Okay, and end. Why is this wrong? This doesn't work. Okay, so that's the first problem. Yes, I have to return some V, not just V, but I have another problem. Look at this error. What does it say? It says you don't need this pattern, which means that all the cases covered by this pattern was already covered before. But that sounds weird, right? Because it sounds like I haven't covered some cases.
We should change K to different object.
Yeah, so basically here, this K is not the same as this K. This is the K that I'm using in my pattern matching. So I'm saying if you can write M as a pattern that looks like this, then return V. It doesn't remember that this K should be that K. That's not something that happens here. I'm just defining a new K now. Okay, so I cannot write it like this. And in this case, actually, Coq catches me because it says that all the cases were already covered by these two first cases of your matching. You don't need the third one. Okay, so again, very important. You cannot write like this. So this is wrong. I call it wrong find. But you can use if, of course. You can use if to check if K and K2 are the same. And if they are the same, then return some V, else return find K M prime. Prove this one, this theorem. So I'm saying for every map M and every two integers K and V, if I search for K after I have updated the value of K to be V in M, then I will get V. I will get some V. Okay, so here I have the map M. I'm saying map K to V. I'm first doing that update. And then I'm saying find K in the updated map. And I expect to get the value of V back. But I want you to prove this as a theorem. And as a lemma, you can add this lemma, which basically says that for every A and B that are natural numbers, A is equal to B. So if I use A equal question mark B, which would give me a Boolean instead of a proposition, the Boolean it gives me is true. This is actually something that you can prove using the techniques that we've seen like in the very first Coq session, but I don't want you to prove that. I just want you to use this lemma. So basically the lemma is saying that equality is reflexive on natural numbers. Ooh, no. Well, what is this? No. This is completely wrong. For every A that is a natural number, A is equal to A. I don't know why I had A and B. I was saying every natural number is equal to every other natural number. That was a bug. Yeah. Yeah. Try to prove this theorem. Okay. Let's see how we can prove this. So this is my goal. I want to prove that for all M's that are partial maps and K and V that are natural numbers, I have this equality. So basically, if I take the map M and I insert KV into it, and then I search for K, I should find V. Okay. So in our proof, we of course first do intros so that I put all of these variables up there instead of having them in the goal. And let's just do simplify. Okay. So I do simplify. And this is what simplify gives me. And again, this is just applying the definitions of find and update. And of course, the right-hand side, there's no way to simplify that. That's as simple as it is. Okay. So basically, it says that if K is equal to K, then some V, else find KV. But I know that K is equal to K because I have this lemma here, which says that everything is equal to itself. So I'm just going to rewrite based on this lemma. So, and when I rewrite based on this lemma, you see that it just understands that k equal to k is true, and because it's true, you will have the then parts. You will just have some v. So you get some v on both sides, and then this is reflexivity. Okay. So before we end this part of the course, I just have to tell you one more thing. If you define a lot of different theorems and lemmas and definitions and so on, it might be that you forget the name of a theorem. You actually have a function called search. Well, not a function, a vernacular command called search that you can use to search for something that you have defined. So for example, I can search for rev. And it tells me that, well, you actually have this theorem called rev length. And this is what the theorem says. So it basically finds all the theorems and lemmas that have rev in them, the word rev. I can also search using a pattern. I can say, I remember that I had proven something that was of this form. Something plus something is equal to something plus something. And I ask it, give me all the theorems that have something matching this pattern in them. And I do it, and it tells me that, well, you have this theorem called nat at com, which basically says that for all a and b, a plus b is equal to b plus a. So this is, and it also says that there is this theorem or lemma, which is actually in the standard library, which has something similar. So let's see what this one says. It says for every x1, y1, x2, and y2, if x1 is equal to y1 and x2 is equal to y2, then x1 plus x2 is equal to y1 plus y2. So that's a theorem that you have in the standard library, and you can just use it. Okay, let's finish what we had for partial maps, and let's finish talking about lists. I now want to talk about something called polymorphism. And again, I try to give you examples based on what you've seen in C++, because that's probably the language that most of you have seen before. And you told me that most of you haven't seen any functional programming language before. So polymorphism, at least the way we're going to use it in this course, which is like parametric polymorphism, is very similar to how templates work in C++. So in C++, if you have a vector, you can define a vector of integers, you can define a vector of floats, you can define a vector of objects of any type, right? So let's say that I want to do something similar here. I've already seen how to define a list of natural numbers, but let's say I wanted a list of Booleans. I don't want to have to just define a new type for list of Booleans and then another new type for, I don't know, list of integers and so on. I want to just define list and be able to have lists of elements of any type. Okay. And this is where polymorphism comes in. And basically the idea of polymorphism is that you have a type or a function that can work on inputs or parameters of many different types. Okay. So here's how I define a polymorphic list, for example. Remember, previously, when I was defining a list, the list itself did not have any parameters. So look at this. This was the definition of NatList. I just said that NatList is a type and it has two constructors. But here, what I'm saying is different. I'm saying that this list is itself kind of like a function that takes a type and gives me another type, okay? Or another way of looking at this is that I have a parameter x, and x is a parameter to list, but it's also a type itself. So for any given type, I can create a list of that type. So instead of x, I can put natural numbers, I can put Booleans, whatever, and I will just get a list of natural numbers, a list of Booleans, and so on. Okay, so I have a list of elements of type x. Now, how can I define this? Again, I want to use the same definition as before. I want to say that either my list is empty or it's obtained by adding a head element to another list. So I show the empty list with nin, and I show the other case with cons. And here's the part where things get really interesting. So cons has two parameters. The first parameter I call little x, is of type big X. Okay, so I'm using this parameter here as the type of this parameter here. And then I also have the rest of my list, let's say my tail, which I call L. And what is the type of L? This is list X, right? Because list itself is defined, of course, recursively, but list needed a parameter. So I cannot say L is just a list. I have to say L is a list of type X. So this is how I can define a list of any type. So now, instead of writing nat list, which was the type I had before, I actually write it like this. I say list nat. So I'm giving nat, which was itself a type, as a parameter to list. Let's look at nil. What is the type of nil? Actually, sorry, maybe I should have done check nil first. So nil was a constructor in my list. And if I check the type of nil, you see what type it has. Right? So basically nil says that for every X that is a type, nil gives me a list of type X. And what is that list of type X? It's just the empty list. Right? And okay, let's do this again, check list. So list is of this type, it takes a type and gives me another type. Nil is of this type, it takes X, which is a type, and gives me a list X. And it does it for any X that is a type. Okay. Now, what happens if I look at nil nat? So remember, I can give a type X to my list. So I can give the same type X to nil. So nil nat is actually going to give me a list of natural numbers. Okay. Or here's another example. And by the way, this is the empty list, of course. Nil nat is the list of natural numbers that is empty. Now, if I want a list of natural numbers that only has the number 3 in it, how do I write that? Well, I have to take nil nat, which was the empty list, and I have to use cons. But now cons actually needs 3 parameters. Cons needs this parameter here, which is the type, and then it needs this parameter, which is the head of the list, and it needs this parameter, which is the tail of the list. So I have to write cons nat 3. So this is the name of the constructor. This is the type X here, which is natural numbers. This is the head, small x, which is 3. And this is the rest of the list, which is the empty list. But again, even nil has a parameter, which is this X. I have to give it that parameter, which is in this case nat. So this is now how I write it. And basically, this is how I represent a list that only has the natural number 3 in it. Okay, and I can again check cons itself. This is also interesting. So what is the type of cons? What is cons? It says that for every type X, for every type big X, cons does this, has this type. It's a function that takes something of type X and something of type list X and returns something else of type list X. Okay. Now, if you didn't understand any of those parts, if you didn't understand from here to here, basically, that's fine. As long as you understand how this one works. Okay. So basically, I'm defining my list, and I can define my list and use one of the types as a parameter. I can say I have a parameter X, which is itself a type. And then I can use X in the definition of my constructors. That's the most important thing you should understand here. Okay. Now I want you to write these functions, which are basically the same functions that we saw for NatList. So I want you to write a repeat function. Now, what does the repeat function do? This is also a polymorphic function. So I want okay, recall how repeat worked before. It took one item and it took a count and it just returned a list that had repetitions of that item, right? But it could only do that when the item was a natural number. Now I want to say, instead of that, let's say I have a function repeat that takes a type X and it takes a value small x of that type, and it also takes a natural number count, and it returns a list of elements of type X, which would basically have this many copies of X. Okay, write this function. Again, the really interesting part here is that one of my parameters is itself a type. Okay, so let's do a pattern matching on our count, on the number of times that we have to repeat this. First of all, if count is 0, I want to return the empty list. So I want to return nil. But I still have to write nil x. I cannot just write nil. Okay, because my list always has a type associated with it. There's no such thing as a list. Think about it like this. I either have a list of natural numbers or a list of Booleans or so on, but I don't just have a list. So I cannot just return nil. I have to return nil x. And the other case is that if my count was basically count prime plus 1, then what I do here is that I first repeat x count prime times, but again, my repeat function now takes 3 different parameters. It takes big X, small x, and count prime. And then I have to do cons of small x with that, but again, cons takes 2 parameters. It takes the type, big X, and it takes the value, small x. So I have to write it like this. Okay. Great, now that we have defined this, we can actually do some computations. So let's say I want to call the function repeat, and I say that the type of the element that I want to put into my list is nat, natural number. And the element itself is 4, and I want to put it there 5 times. Okay, so I can say repeat nat 4, 5, and I compute that, and this is what I get. So the type of the output is a list of natural numbers, it's list nat. Okay, and the output itself, you see that it's const nat 4, const nat 4, so on. So every const is not only taking the parameters that it took before, but it's also taking nat as a parameter. Okay, and of course, at the end, we have the nil, which is the empty list, but even that is not just nil, it's nil nat. Okay, now what happens if I write check repeat? What is the type of the function repeat? This is the type of the function repeat. So it says that for every x that is a type, repeat takes a value of type x, and it also takes a natural number, and it returns a list x. Okay. Great, but this is now too cumbersome, because I mean, of course it makes sense, and of course we could define a list which could contain elements of any type, and now we can also define maps that map elements of any type to elements of any other type. But this is not great, especially this kind of notation. This is really hard to read for humans. And also, I don't like to have to constantly write the type here, right? So I want to simplify my writing. Let's see how I can simplify my syntax and write this function in a simpler way. So this is my function repeat. Look at the header of the function here, and look at the header of this variant of this function, which I'm calling repeat prime. So when I was defining repeat, I said that I have these parameters. I have x, which is a type, small x, which is of type big X. I have count, which is a natural number. and I return a list X. Now here in the definition of repeat prime, as you see, I'm removing all of the types. Right? I'm just saying repeat prime takes big X, small x, and count, and returns a list X. Okay. Why can I remove all of this? Because Coq is smart. Coq can understand from the rest of this definition what the type of every one of these elements should be. So for example, I'm returning a list X. If I'm returning a list X, that means X should be a type. So I don't need to tell Coq that X is a type. Coq knows that this X is a type. Right? Similarly, I'm returning a list X. And for example, here I'm doing cons XX. So if I'm doing this, it means that small x is of type big X. Otherwise, I couldn't even call cons on that. Right? So Coq understands that small x is of type big X. I don't need to explicitly tell it. The other point, how does it understand that count is a natural number? Well, I'm doing a match on count, and I'm saying if count is 0, well, only a natural number can be 0. Or I'm saying if count is the successor of count prime. Again, this S was something that was defined only for natural numbers. So Coq is smart enough to basically do type checking and figure out what the type of all of these variables are. And I don't need to write the types of the parameters. I can just write my function in this simplified form. Okay? And again, if I check repeat and check repeat prime, they have the same type. So you see the Coq could actually understand what the types of all of these parameters in repeat prime were supposed to be. Okay. But still not good enough. Let's try to simplify this a little bit more. So another thing that I can do is that I can put an underline. And when I put an underline, what I mean by that is I'm telling Coq to figure it out. Okay? So I'm not going to write the type X. I'm just going to put an underline instead. And Coq understands that it has to figure this out. It has to figure out what type to put there. Okay? So this is, again, repeat double prime. This is the same function as repeat prime, except that I'm saying when it's 0, return nil. And then I'm putting an underline here. What this means is that I know that I have to return nil of some type. But I'm too lazy to find it, so I'm just telling Coq, figure this out. Figure out what type of nil you have to return. And again, Coq knows that this function is supposed to return a list X. So this function can only return list of elements of type X. So if I want to return a nil list, I have to return nil X. And the same thing here. I can say that, well, figure out the types. So previously I was saying cons X of X and repeat X of so on. So instead of all these big X's, I can just put underscores. And again, Coq understands what to do with this. So I don't know why it's not executing. Okay. So again, if I check repeat prime, which was the previous function, this was the type. And if I check repeat double prime, the type remains the same. So again, Coq could figure out the details and fill it in. Okay, but this is still really awkward. Because right now, if I want to just create a list that has the elements 1, 2, 3, this is what I have to write. Right? So I have to say apply cons, and I don't give it the type. I tell Coq to find the type itself. But anyway, I have to apply cons to 1 and then apply that. Like basically, let's start from the inside. I take the empty list. I add 3 to the beginning of it. Then I add 2 to the beginning of that. And then I add 1 to the beginning of that. And every time I'm telling Coq to figure out the type on its own. But anyway, this looks ugly. I have to put so many underlines and I have to write cons so many times. I need so many parentheses. It's ridiculous, right? But okay, if I check the type, you see that Coq actually found the type correctly. It's a list of natural numbers. And if I say print it, it prints it, and it says it's a list of natural numbers, and this is what the list is. Okay. So here's the part where things get actually interesting. I can have implicit arguments. And I can have implicit arguments when I'm defining a type in the constructors and also in functions. Because to be honest, constructors are functions. Okay? So here's the thing. I have nil here. Where is it in my construction here? And this nil takes one parameter, x. Okay? But what I can do is that I can write something like this. I can say arguments nil and then curly braces x. So whenever I put something in curly braces, I mean that it's implicit. I mean that I will never write it, but I expect Coq to always figure out what it is. Okay? So basically it's like I'm always going to write this underline, but I'm saying I'm not even going to put the underline. You have to figure out what x is. And if you can't figure out, you have to just give me an error. And that's what Coq does. So I'm saying whenever I write nil, instead of writing nil x, I'm just going to write nil. And you have to find x on your own. And the same thing for cons. I'm saying whenever I'm writing cons, here, I'm not going to give you x. I'm just going to give you small x and l. And you have to figure out big X on your own. And I can do this even for this function. I say that in this function repeat, I'm never going to give you this parameter x. This is an implicit parameter, and you have to figure it out on your own based on your type system. Okay? So this is how I say all of these are implicit. And again, we use curly braces for implicit parameters, and we use normal parentheses for explicit parameters. Okay. Now, if I do this, you see, when I wanted to create the list of natural numbers 1, 2, 3 before, I had to write cons and then I had to write the type or underscore every time. But now I don't have to write the underscore anymore. I can just define something like this. I can say my list is just cons 1, cons 2, cons 3 nil. Okay. And here's the thing. I can check the type. And again, you see the type is correct. It's a list of natural numbers. So Coq could actually resolve the implicit parameters on its own. And I can print it. This is what it is. And of course, this is the same as the previous list. You can see that. Okay. Now, another way of doing this, another way of having these implicit parameters is to just define them as implicit already when you're defining your function. So here I'm writing yet another repeat function. And you see the difference is that implicit parameters are in curly braces, explicit parameters are in normal parentheses. Okay, so I'm saying this function repeat, it's going to take an x, which is a type, but it's going to be implicit, which means that I will never provide it. And every time Coq has to find x on its own. And then it's going to also take a small x, which is of type big X. It's going to take a count, which is a natural number, and it's going to return a list of type X. Now, how does the function work? Again, I look at my count. If my count is 0, I'm going to return the empty list. I'm going to return nil. But see, I'm not putting any types here after nil because I've already told Coq that the X in nil is going to be implicit. So Coq knows from now on that whenever I write nil, it has to figure out nil of which type. Okay. And here it's again the same thing. It's much more simplified now. So I say that if count is count prime plus 1, then you just repeat x count prime times. And you see I'm calling the same function recursively, but I'm not giving it big X. Because big X is implicit and Coq has to figure that out on its own. And then I'm putting small x at the beginning. And again, for cons, I'm not giving it big X because big X is implicit in cons as well. Okay, So now finally, this looks like something that can be called kind of human readable, right? If you're a human with a lot of experience with Coq, you can read this. And I don't have to just keep repeating my big X everywhere. Okay. I've shown you the solution already again, but write this function now. Write a function that basically does append. So it takes two lists and gives me another list, which is basically the two original lists glued together. And again, I want this to work on lists of objects of any type. So I will have an implicit type as a parameter here. Okay. So we're going to do what we did for lists of natural numbers, except that now we're doing it for lists of any type, right? So I'm going to say, do a pattern matching on the first list. And if the first list was nil, and actually, you know that this is nil X, but I'm not writing the X because that's implicit now. If it's nil, then return the second list. Otherwise, if the first list is of this format, and again, I'm not writing the X because X is implicit. If it's const HT, so this is the head, this is the tail list, just append the tail list to L2 and then put H at the beginning. Okay, great. Now write reverse and lengths. Okay, I'm going to go kind of fast here. So reverse is again exactly like before. I look at my list. If it's the empty list, and again, this is nil X, but I'm not writing the X anymore, then I return the empty list. Otherwise, if it's H and some tail, I first reverse the tail, and then I call append. So this is just a list that only has H in it, right? And this is the reverse of the tail. So I append the list that only has H in it to the reverse of the tail. And for lengths, again, I have a very similar situation. I say if my list L is empty, if it's nil, return 0. Otherwise, if it's something followed by L prime, just take the length of L prime and add 1 to it. Give me the successor of the length of L prime. Okay. So this kind of implicit parameters or implicit arguments, they really help us write simpler code. But now we have some problems. So for example, if I write something like this, if I say I want to define a variable X and I want X to be nil, this one will give me an error. Okay, and look at the error. It says the term contains unresolved implicit arguments. Okay, more precisely, it says that nil, it was a constructor for list, right? So nil is supposed to be a list, but it has to be a list of some type X. But it doesn't know how to find X, cannot infer the value of the parameter, the implicit parameter X, right? And the reason for this is that there is no context here. If I'm just saying X is nil, I'm saying X is the empty list. But I have to say, is it an empty list of integers? Is it an empty list of Booleans? So what is X? What is big X? And this is something that Coq cannot find on its own, so it gives me an error here. Now, one way around this, of course, I cannot write this because that gave me an error. I'm going to comment it out. But one way around this is to actually tell Coq more information. I'm going to say, instead of just defining the variable X to be nil, I say I want to define a variable X, which is of type list nat. And then I say this variable X is nil. Now this one passes. because Coq understands that this implicit type that had to be passed to nil is supposed to be nil nat, right? Because it's supposed to be nat, actually. So I'm saying I have a list of natural numbers called x, and it's nil. So of course, it has to take the empty list, but it has to take the empty list of natural numbers, because otherwise the type doesn't match. So you see, it's smart, but you have to make sure you're giving it enough context. Now, what if I don't want to do that? Well, what if I want to use the explicit version of nil? Okay, so for example, if I say check nil, okay, you see it's much more complicated. But I can write at nil. Okay, I can say y is at nil. And at nil means the explicit version of nil. Okay, so now if I check the type of y, or if I check the type of at nil, you see that I get the type that I used to get for nil when it was explicit, when it was not yet implicit. Okay, so why is this useful? Because I cannot write nil nat. Okay, so if I write check nil nat, that gives me an error. Why does it give me an error? Because the parameter of nil, the type big X, was supposed to be implicit. If I give it explicitly, Coq doesn't understand that. Coq just thinks that it has to find the implicit parameter, and this is another parameter, right? But I can write at nil nat, and then this means that I take the explicit version of nil and use the parameter nat for that. And of course, that's a list nat. Okay. Anyway, this is not very useful, but it's just like, if you made something implicit and then you wanted to make it explicit, you can do it with a nat. Okay, but let's define our syntactic sugar, because of course we need this, otherwise our code is going to look really ugly. So again, I'm going to define this double colon to mean cons, and this is exactly the same as before. I'm going to define this notation for the empty list. I'm going to define this notation for just writing a list by its elements, and I'm going to define this one as append. So let's prove the same theorem as before. Let's prove that append is associative. But look at this theorem. What does this theorem say? This is actually now a polymorphic theorem. I'm saying for every X, for every type X, and for every three lists that are lists of elements of type X, I have this. I have that list 1 appended with list 2 appended with list 3 is the same as first appending list 1 and list 2 and then appending list 3. So another way of looking at it is the way that it's written here. So it says for every X that is a type. I just wrote for every X, but Coq itself could understand that X is a type. For every X that is a type, and for every three lists that are lists of type X, I should prove these things. So my proof is very simple. It's basically the same proof that we had for lists of natural numbers. So I'm going to go over it really fast. I do intros, so all of these things go up there. And then I do an induction on list 1. And I have the base case of my induction, which is the case where list 1 is empty. And this one is just solved by simplifying and then doing reflexivity. And then the other case I have is the inductive case, inductive step. And here again, I can first do simplify, then I can rewrite using my inductive hypothesis, and then the two sides are the same. I can do reflexivity. You can go back and revise this, but again, it's exactly the same proof that I had for lists of natural numbers. The only difference is that instead of having lists of natural numbers here, I have a type X, which is always up here, and I have lists of type X, but I'm doing the same thing on it. Okay. Now, in the same way as before, I had options before. I can now define polymorphic options. And this is also something that exists in the standard library of Coq. So I can say for every two types, X and Y, I define a new type called the product of X and Y. And the way it works is that every element of this product type is a pair where the first part is, the first parameter is a small x of type big X, and the second parameter is small y of type big Y. So this is just Cartesian product. Okay. And then again, I say that in this definition of pair here, both X and Y are going to be implicit arguments. So I'm never going to write these types. Okay. And I also define some notation. I say, for example, if I write X comma Y inside the parentheses, that's the same as writing pair XY, because I want to have a simpler notation. And I want to say that if I have two types, X and Y, and I write X star Y, that means the product type of X and Y. Okay. And what this part means is that I'm saying if these are types, then use this product, because I don't want to redefine the product of integers, for example. I want to keep the definition that I have for that. Okay. Now, but anyway, it says that you already have that also in the standard library. So I'm just defining it again. You don't need to define it. It's part of the standard library. It works. So now I can have the same functions first and second, which I had before. Remember, first took a pair, but now look at this. So first is going to take two implicit parameters, which are the types X and Y. So it's a pair where the first element is of type X, the second element is of type Y. But X and Y are implicit parameters. And then I have this P. What is the type of P? It's the product of X and Y. Remember, product of X and Y is another type. Okay? And I show it like this. And what is the type of the response? What type does this function return? It returns an element of type X, because the first element is of type X. And again, this is a very simple pattern matching. I say that if P is basically XY, just return X. And for second, it's exactly the same thing, except that my return type is Y. And if I have a pair XY, I return Y. Okay, nice. So here's another function which we normally use. Oops. And this is called the zip function. And sometimes actually people call it combine, depending on which functional programming language they're used to. So let's say that I have two different lists. I have LX and LY. And let's say that LX is a list of objects of type X. And LY is a list of objects of type Y. And I just want to zip these two lists together, which means that I want to return a list of pairs where the first pair is the first element of the first list and the first element of the second list. The second pair is the second element of the first list and the second element of the second list, and so on. Okay? So my return type is going to be also a list, but every element in this list is a pair, where the first coordinate is of type X and the second coordinate is of type Y. And again, as before, I have two implicit parameters, X and Y. And of course, these implicit parameters, they're types. So I can write it like this, but I don't need to tell Coq that these are types. Coq understands that these are types. Okay, but how do I actually write my zip function? I say, look at these two lists that you have. First of all, if any of these two lists is empty, you're going to just return the empty list. So this one says that if the first list is empty, return empty. If the second list is empty, return empty. Now, very importantly, this one is different from this one. This is an empty list of type X. This is an empty list of type X times Y. But again, Coq is smart enough to understand this. And this is, of course, an empty list of type Y. Okay. And finally, if none of my lists are empty, let's say that I break the first list into an element head and a remaining list tail. And I do the same thing for the second list. So I have a head X, tail X, head Y, and a tail Y. So I say recursively zip the two tails together and then add this pair at the beginning, add the pair HX, HY at the beginning. Okay, so I do that. And now I can compute something like this. I can say compute the zip of 1, 2, and 3, 4. And if I do this, what will I get? I will get a list of pairs of natural numbers. And the first pair is going to be 1, 3, and the second pair is going to be 2, 4. So this is what I get. You see, it's a list of nat times nat. And every element of nat type times nat is a pair of natural numbers. Now, I don't have to necessarily have the same types to zip. So I can say, take true, false, and let's say 2, 4, 5, and zip these two. Okay. Oops, sorry, I had to use a semicolon. I don't know why I used the comma there. Okay. Now, if I do this, I get a list of pairs, and it's true 2 and false 4. And by the way, it ignored the last element of this one because this second list was longer than the first list. And in my definition of zip, I said that whenever one of the lists runs out, I just stop zipping. Okay. Great. So now the next thing that we're going to see at the beginning of next session is how to do polymorphic options. And of course, it's going to be very similar to what we've done until this point. Okay, great. See you on Thursday.